This lecture is going to go over the topics of empirical and molecular formulas. And this is really the start of a subject of chemistry called stoichiometry. And stoichiometry is the study of quantities of materials consumed and produced in a chemical reaction. And so one of the things we're working towards in the course is being able to understand and predict chemical reactions. And stoichiometry is sort of the math associated with chemical reactions. Okay, and so when we start to talk about balanced chemical reactions, some things we want to be able to answer are, this idea of if we have a reaction take place, how much of a given product can we make? Or how much of a starting material do we need to make a certain amount of product? And then at the end, we'll start to talk about how much energy is required or released for a chemical reaction to occur. But before we can get to these, we need to back up and start to better understand a molecular compound's elemental composition and chemical formula. We need to be really good at going grams to moles and vice versa for molecules. And so we're going to take a little bit more time to understand a little bit more about molecular formulas. And we're going to start by introducing a concept known as the percent composition of compounds. And this percent composition of compounds, this is how we know what a lot of molecules are. This is one of the analytical techniques we can use to determine how much of each atom is present in a molecule. And so what this is when we think about a chemical compound, we can describe it by the numbers of its constituent atoms, the molecular formula, or we can describe it by the percent composition, the ratio of masses of atoms to the molecule. And the key is when we're drawing and writing molecular formulas, right, this is a model to represent the molecule. In the lab, we can take a molecule, we can take a solution or a compound, put it in an instrument, and determine the percent composition. This is experimentally how we determine what's present. And from these results, we go back. So from this experiment, we can then come back and say, oh, I know what the molecular formula was. So the mass percent then, also called weight percent, is the ratio of mass of an element in a molecule to the mass of the entire molecule. So in a formula, the mass percent of element X is the mass of that element X in 1 mole of the compound over the mass of 1 mole of the entire compound times 100 to make it a percent. And so let's look at an example of this. We can look at, this is the molecule acetylene. And so if we look at this molecule, it's a fairly simple molecule, HCCH, and we can calculate the mass percent carbon and hydrogen present. Okay, and the way we would do this is we'd start off and say, let's first find the mass of carbon in 1 mole of C2H2. Right? So the way we would do this, we know in this molecule, C2, there's 2 moles of carbon. So if we have one of these, we have 2 carbons. From the periodic table, we know the mass of 1 mole of carbon is 12.01 grams. So this is from the periodic table, right? So this 2 is that 2. This is from the periodic table. And so from that, we know the mass of 2 moles of carbon times its molar mass equals 24.02 grams of carbon. Right. So now we have to find the mass of 1 mole of C2H2. We've done this before, right? This is just finding the molar mass of this molecule. So we're going to add up the mass of all of the atoms present, right? So we get the mass of all of that together would be 26.036 grams. We can write it out in the same way. So 1 mole of C2H2 times 26 over 1 mole, we get 26.036 grams. So if we have 1 mole of this molecule, this is the mass. Of this mass, 24 grams is carbon, and the rest would be hydrogen. So if we're looking to find the mass percent, what we're going to do is we're now going to take our ratio. So to find the mass percent carbon, we're going to take a ratio of 24.02 divided by 26.036. Right, so the mass of 1 mole of carbon in 1 mole over this. And what we find out with, take that back. The mass percent of carbon, 24.02 divided by 26.036 times 100 equals 92.2% carbon, right? And so again, if we took this molecule, if we had a gas cylinder of acetylene and we injected it into our instrument, what that instrument would tell us is this molecule that we injected is 92% carbon, and then the rest would be 8% hydrogen. And from that, we can start to piece together that the molecule must be acetylene. And so we can also find the mass percent of hydrogen, right? So if it's only carbon and hydrogen, we could just do 100 minus this. But if we don't know it's only carbon and hydrogen, then we're going to have to go through the same process. And again, I'll say mass, 2 moles of hydrogen, multiplied by the molar mass, and so we get 2.016 grams of hydrogen. Now we're going to take our ratio of the 2 grams of hydrogen over the 26 grams of acetylene, and we get 7.74% hydrogen. So that would be the mass percent hydrogen. So on this table, what we're showing here is the names of some simple organic compounds. So acetylene, benzene, ethene, 2-butene, and their molecular formula, C2H2, the Lewis structure, the molar mass of each, and then the percent carbon by mass and percent hydrogen by mass. So at this point, you should be able to fill out the rest of this table, right? The way we would get the molecular formula is just by counting the carbons and hydrogens, right? So we could do that and say this is C6H6, this is C2H4, this is C4H8, right? Just by counting what's there from the structure. You should be able to determine the molar mass of each of these. And then we should be able to determine the percent carbon by mass and the percent hydrogen by mass, just like we just did. So I'd encourage you to pause the video, calculate, fill this table out, and then keep watching. So if you've gone through those calculations, this is what you should get. Here's our molar masses, and here's the percent carbon by mass and hydrogen by mass. Now, one of the key takeaways from this is you'll notice these numbers are the same, and these numbers are the same, despite the fact that these are different molecules and these are different molecules. So different molecules can have the same mass ratio, right? When we think about this as chemists, we're concerned with the mole ratio of atoms in a molecule, right? That's the molecular formula, how much of each atom is present, right? So benzene and acetylene have the same by mass ratio. It's both 92% carbon, 7% hydrogen, and yet their molecular formula is different. This brings us to this idea of the empirical formula versus the molecular formula. All right, we want to know the molecular formula. Experimentally, what we find first is the empirical formula. So we have to derive this in order to get the molecular formula. So what is this empirical formula? The empirical formula describes the relative number of each type of atom in a compound. It is given in terms of the smallest whole number ratios. So compounds with the same empirical formula have the same mass percent of atoms. The molecular formula is the exact number of each atom in a compound. It is always a multiple of the empirical formula. So what do we mean by that? Well, let's bring this compounds back that we just looked at. So acetylene and benzene, right? These are the first two in the table in the previous slide. And we said acetylene has a molecular formula C2H2 and benzene is C6H6. Here's the molar mass. So the empirical formula is given in terms of the smallest possible whole number ratios. So what we would do is say the ratio of carbon to hydrogen is 1 to 1. Here it's 1 to 1. So both of these have an empirical formula of CH. So the ratio is there's equal numbers of carbon and hydrogen. So the empirical formula would be CH. If we found the molar mass of just the empirical formula, it would be 13.02. And then we can see acetylene is really 2 times the empirical formula, and benzene is really 6 times the empirical formula. So they're always a multiple of the empirical formula. So how would we use this in a problem? So if we were working in an analytical chemistry lab, and one of the things that might come in is you get a sample and you have to figure out what is that sample. So in this case, we have a sample of a white powder, right? It's sent to us and we want to figure out what is the molecular formula of that. That's the first step to figure out what is this substance. So how can we figure out what this thing is? So we could take some of this white powder, put it through our elemental analysis, and what the instrument would give back to us is the mass percent of elements. So we find out that this is 43.64% phosphorus and 56.36% oxygen. We want to find the molecular formula. So how are we going to do this? How are we going to go from mass percentage to molecular formula? The first thing we'll do is we're going to assume we have 100 grams of a sample. We don't, but it doesn't matter because these are mass percents. And the reason we assume 100 grams is if we assume we have 100 grams of sample, that means 43 grams are phosphorus and 56 grams are oxygen. So 100 grams is just assumed to make the math easier. Once we assume 100 grams, we can calculate the number of moles of each atom, right? Because if we know there's 43.64 grams of phosphorus, we can divide by the molar mass of phosphorus and find out there's 1.409 moles of phosphorus, right? All I did is grams to moles, right? So both of these conversions are nothing more than grams to moles. So now I know how many moles of phosphorus are present and how many moles of oxygen are present. In the next step, I'm going to divide these two. We're going to divide everything by whatever's the smaller number of moles. So because this is smaller, we're going to take both of these and take 1.409 divided by 1.409. And we're trying to get whole number ratios of moles. So we get 1 mole of phosphorus. We're going to then divide 3.523 moles of oxygen by the smaller number 1.409, and we get 2.5 moles of oxygen. Right? So for every 1 mole of phosphorus, we have 2.5 moles of oxygen. That's what this is telling us. For every one of these, we have 2.5 of those. We're then going to turn this into our empirical formula. And our empirical formula is really from these numbers. This is what gives us our empirical formula. So we'd write it as PO2.5. But we can't have half an atom, right? So what we're going to do is go to the smallest whole number integer. So we're really going to take this thing and divide both by 2. And so we end up with P2O5. This is the empirical formula. So what we did was we took the mass percentages and we used them to find the empirical formula. The last step then is to determine the molecular formula. And the one piece of information we need beyond what we have is the molar mass, which can be determined with through measurement. And we can determine what is the molar mass of this compound. In this case, it was found to be 283.88 grams per mole. So all we're going to do is take a ratio of the molar mass divided by the empirical mass. Right? And when we do that, we find out 283.88 divided by 141.94 equals 2. And what that tells us is we have to need 2 of these P2O5 units. So we're going to multiply both of these subscripts by 2. And we get P4O10. This is our molecular formula, P4O10. So again, what did we do? We started off with our mass percents, found our mole ratio, turned into the lowest possible whole number ratio, then divided the molecular weight by the empirical weight, and used that to determine the molecular formula. Thank you.